The purpose of this video is to provide a brief introduction to the Engage Antenna Design Assist application. This is by far the richest and most complex application in Engage. It can provide all kinds of interesting and useful insights, but covering it all in one video would just make the video too long. So this video will just cover the introductory form, the main form, and the others will follow. So if we go to the main menu, click Products, Software Applications, and choose Antenna Design Assist, the main form comes up. Now the purpose of this application is to provide the user a way of studying the properties of the antenna model that's actually in play in Engage, and allow the user to play with certain antenna parameters and see the effect immediately, instantly, on the effect on the antenna pattern. So here's the main form. It has two main panels. The left side shows a physical representation of the antenna inside the radome cavity, and the right side shows the antenna pattern as calculated using the in-play set of antenna parameters. So now looking at the left side, we'll start with the left side. There is an outline shown of a wireframe outline of the antenna. In this case, it's an inverse Cassegrain represented as a reflector antenna, and behind that, or around it, is for reference, is an inverse Cassegrain antenna inside our radome for reference. And if we click on the antenna icon, then the antenna design configuration form appears. And so as we change parameters on this form, we see instantly the effect on the right side. So let's anyway continue with the left side. We can change the position of this graphic in the field, and we can change its magnification. Again, the idea here is to get an idea of how the antenna, as it's designed by the analyst on the form, configuration form, how it fits inside the radome, because you're designing also the radome and the antenna. And it's just impossible to figure out how all these things interact with each other just by looking at this form. So we really need a physical drawing. Now, not that the physical shape exactly predicts the antenna pattern, but we do have to have those things correct. So anyway, on the left side of this panel, there's a control that controls the view that you see of the antenna and radome. Right now we're looking at a top view. So if we use this orange button here, we can scan the antenna inside the radome. And notice that the motion is a bit jerky, because each time the azimuth position of the antenna changes, the antenna pattern is recalculated. So to smooth things out, if you uncheck the live button, then the antenna pattern is not updated as soon as each time as the controls are adjusted. So here we can yaw the antenna back and forth, and if we look at the side view, then it's, arguably a little bit more interesting. This illustrates something I think is interesting. The effect of, we'll switch over to the right side in a second, just for a minute, but each one of these little magenta dots or crosses on the reflector surface is the position of one of the integration patches on the reflector surface used for calculating the antenna pattern. If we change the look angle, the beam position, to 90 degrees, then we get a nose-on view or front view of the reflector. And if we now change the number of the spacing of the integration patches, which is here, and this control right here, this integration patch separation. So if we'll increase the separation, we get fewer patches. I think things get much more interesting if we go to a live antenna pattern and then we change this control. There's not enough real estate here to really show you everything that's going on, but if we change the integration patch separation, we can see instantly the effect on the null depths and side lobe levels and antenna gain as well. So if you were trying to decide where to set this, you can make it very dense if you want to, but it's going to slow things down a lot. If we were trying to set this parameter, we can instantly see what the effect is on the antenna model, antenna pattern, that would be used in the Engage simulation. By the way, moving over to the front right side just for a second. As we change parameters, there are some metrics that are shown at the top here, top left and top right. That, for example, the half power beam width in the azimuth plane, we're looking at an azimuth plane cut here, some channel peak gain, azimuth difference gain, and so on. You can read them down the list there and where the track points are as they have been found. So I will click Reload Current Model, and we're back to where we started. Let's zero the yaw position, and okay, let's go back to the antenna configuration form. Now, as we change the antenna type, the graphic and the antenna pattern is updated immediately, instantly. Here we have a flat plate array, and so if we change the yaw position, the antenna pattern you get, by the way, corresponds to whatever the parameters are set at on the antenna configuration form. And this is not set up for, well, as soon as I click the antenna, that icon, we go back to the one we were at. But if we go to a flat plate array antenna, then the graphic changes and so does the antenna pattern. But this is not a proper flat plate array antenna model. It's not configured for that. But if I click, see, look, see, the antenna pattern is a mess. But if I click Save, Create and Save Default Model, if I go past the warning thing, then we get the proper default flat plate array antenna model. So that's zoomed a little bit too much. Let's go off live here. Zoom that out, and so as we change the beam position, you can see it's interesting too that the relationship between the scan angle for an inverse Cassegrain antenna and a reflector or a flat plate array antenna is a 2-to-1. And if we go to a top view, we can see that as the twist mirror in the inverse Cassegrain is twisting at half the speed of the flat plate array. Same thing, by the way, for the reflector antenna. If we click Create and Save, we'll go back to the original model we were using. And as we scan the beam, the twist mirror moves at half the rate of the reflector. Now we can see something interesting if we change the antenna model from a reflector type to a mirror scan antenna. So select that, click Create, Save, and Create and Save Default. Now this antenna is a mirror scan antenna. It's a little bit bigger than the last one, but we want to see it up close anyway, so we'll just change the offset a little bit. Now in this type of antenna, the feed is fixed and the reflector is gimbaled. And so we'll uncheck the live antenna model here, so we can scan the mirror. So now see the mirror scans, or excuse me, the reflector scans, and it scans at twice the speed of the twist mirror in the underlying inverse Cassegrain antenna. So the reflector is scanning the same way as the reflector type antenna, but the feed is stationary. The feed is, by the way, this orange and yellow thing in the center here. The red boxes with X's in them are the positions of the monopulse feed seen from above. This is a top view and it's squinted, so we get a sum and difference pattern. And the yellow X is the position of the focus of the reflector when it's in its zero position. If we move the reflector, we see this feed stays stationary. This is different from the reflector type antenna. Now I haven't reconfigured, but we just want to see the relationship between the feed position and the reflector position. When we have a reflector, a rear-fed reflector, the feed scans with the reflector, and for a mirror scan antenna, the feed stays stationary. So let's go back to the reflector type antenna. There is a refresh all button which refreshes all of the visual fields. Sometimes little black squares appear and you can get rid of those. The last visual piece in the top level form is the view aperture illumination, which is not finished yet, but the intention is to show the user the E-field distribution over the antenna aperture in centimeters across the dish for tailoring the antenna pattern, but it's not currently operational. Now, still sticking with the left side, we can choose between a black or white fields, depending if you wanted to do a screen capture or something. We can decide whether the radome is present or absent. So the antenna pattern changes instantly. This is the effect of the radome on the antenna pattern. We can also change the radome position. So we can change the, if we look at a side view and we use this control, this elevation, radome elevation position, and we change it, we can tip. It's like tipping a flight table up or down. And this, although it has relatively little effect on the copolar pattern, it can have quite a dramatic effect on the cross-polar pattern. And we can also, if the radome is present, it will have an effect. Depending on the antenna type, it may have an effect even if the radome is absent. At the top here, we have another control that defines the pattern scan type. Previously, in another video, we talked about two different ways of measuring the seeker antenna pattern. One way is to pin the seeker antenna at a fixed angle and scan the body and the body, meaning the radome and the antenna, as a single unit. Alternatively, although it's harder to do, you could keep the radome stationary and scan the antenna behind the radome. And so this control allows you to choose between those two. So we can see the effect of scanning the antenna behind the radome or the body and radome together. By the way, if we choose a body scan option, notice that the azimuth position for the radome becomes disabled because you're doing a yaw scan. If you change it to antenna type, scan the antenna behind the radome, that control becomes available. And if we look at the top view of the radome antenna and we change this, then we see the radome changing its position. So we can zero that. Now on the right side, we have the antenna patterns, which is the business part of what we want to look at. So we can choose the graph width, and we can pan the antenna, the pattern. We can choose to enable or disable the sum pattern or azimuth difference pattern. We can look at the power pattern or the E-field pattern for more advanced purposes, and we can change the dynamic range here so you can get a better look at whatever it is that you wanted to look at. So go back to power patterns. We can choose to look at an azimuth cut, an elevation cut, not very interesting in this case, a positive diagonal cut, and a negative diagonal cut. And again, we can choose between black or white fields. We can also change the point separation. Right now it's 0.2 of a degree. Oh, by the way, I forgot to mention the Azimuth Discriminator. Now, that one is run by a radio group instead of a checkbox because visual clutter becomes a problem, but we can either get rid of the Azimuth Discriminator. I'll get rid of all of them at the moment. We can look at the Azimuth Discriminator or the Elevation Discriminator. Unsurprisingly, an azimuth cut of the elevation discriminator is not very interesting, but if we went to an elevation cut, it's a little bit more interesting. So we'll go back to an azimuth cut and we'll show the antenna patterns again. Now, at each time the azimuth discriminator, or any discriminator, crosses the zero line, that's where potentially a track point is. And so if there is a stable track point, reference to the slope of the discriminator at bore site, then a black marker is drawn. Then we can change the size of those markers using these controls down here just for visual reasons. And I'm going to make them a little bit bigger here because I want to show something. Now there are two other controls here. Show control loop markers. If we check that, then each circle representing a stable track point has drawn over it an X and a horizontal line. And the meaning is this. I'll make these bigger so you can see them even better. The X represents the natural frequency of the control loop at that track point. And if that natural frequency is larger than the control loop for the copolar bore site track point, then the arms of the X are bigger than the diameter of the circle. That would mean that the natural frequency at that track point is higher than the copolar, than what the designer intended. The horizontal line represents the damping ratio. If the damping ratio is the same as that of the copolar track point, bore site track point, then the horizontal line touches the outside of the circle. If it's smaller, then the damping ratio is less. So a higher natural frequency means a twitchier loop. A higher damping ratio means a less ringy loop, and conversely. If we click Show Control Loop Labels, this, and I'll get rid of the azimuth difference pattern because it's cluttering things a little. Now the natural frequency, damping ratio, and the discriminator slope are shown at each track point, because it's impossible to figure this stuff, or very hard to figure this stuff out otherwise. So sure enough, the natural frequency on Boresight for this case is 2.24 hertz, and we see this X drawn a little bit bigger than the circle for the first left track point, and yep, its natural frequency is 2.61. The horizontal line is a little bit less than the diameter. Its damping ratio is 1.18, and the Boresight one is 1.37. So anyway, it creates a little bit of clutter, but under certain circumstances, it's potentially useful for the analyst. So, okay, let's make those markers smaller again. And we can set also the discriminator saturation voltage using this control. Okay, so that's pretty much covers the story for copolar antenna patterns. We can also look at cross-polar antenna patterns. So moving to this control group down here, the antenna pattern calculation group, the radiation pattern right now is calculated for horizontal polarization, and this antenna is horizontally polarized. If we go to vertical polarization, we now look at an azimuth cut of its cross-polar antenna pattern. Unsurprisingly, we don't see anything. The reason is the gain is so low. So if we provide an offset, we see, yep, there is, it's just very low. Or, alternatively, if we increase the dynamic range, we'll see the cross-pole pattern poke up there. So, however, if we were to change the body tip angle, like tip the antenna pattern up, for example, or excuse me, the radome up by a little bit, we see unsurprisingly, we see the cross-polar antenna pattern appear. We can see the azimuth difference pattern as well. So the difference pattern looks like a sum pattern, and the sum pattern looks like a difference pattern, exactly as should happen for an azimuth cut of the antenna patterns. So although the radome tip angle doesn't have much effect, look at a side view here so we can see the tipping of the radome antenna radome together. Even though it doesn't affect the copolar pattern very much, it has a big effect on the cross-polar, an azimuth cut of the cross-polar pattern. We can also see how the discriminator track points are changing as the body tip angle changes. And in a minute, you'll see the second left track point change. Well, it's growing now. And we see track points on either side of Boresight. So let's go back to 0 radome pitch. And let's look at near cross-polar patterns. So we're at cross-pole now. If we change this control, we start changing the polarization angle, and the azimuth cut of the antenna pattern changes very dramatically as you change the polarization away from perfect cross-pole. Like let's see if I can get this close enough. There's perfect cross-pole, minus 0.10 of a degree. Here's how the cross-pole pattern is coming up, and how the track points are changing. At cross-pole, notice that we have track points on either side of Boresight. So if I change the azimuth scale, there they are. This next clip shows the effect of a polarization swing from minus 3 degrees to plus 3 degrees and back to minus 3 degrees relative to perfect cross-pole. For a body pitch angle of plus 3 degrees, previously the body pitch angle was 0 degrees, which isn't very realistic at all. So we can see the track points move around in the cross-pole. Some indifference patterns bounce up and down as the polarization swings near perfect cross-pole. So we'll go back to copole. We can also adjust the pin angle of the antenna. If we were using a body scan type antenna pattern, then we can set the pin angle of the antenna behind the radome, like so. And I'm changing the yaw angle, so if we look at the top view, then this is changing the yaw position of the antenna, although it's not reflected in this graphic for some reason. And we can also change the elevation angle of the antenna, which for some reason doesn't appear to be updated also, but these are minor issues. So I'll go back to, let's zero these things out, and zero that, and go to an antenna scan. There we are, and we're back to where we started. I see a couple of black bars, refresh all, and so this is a summary, a brief summary of the main features of the Antenna Design Assist application in Engage. Now there's more applications underneath this. This is by far the richest and most complex application in Engage, and the next one we're going to look at is map track points, but I'll put that in a separate video. So this concludes this introduction.